So in this part of the lecture, we will look at an example where we will pick up a regular LP problem and try to convert it to our standard form. Here is a transformation example. Let's assume we are given to minimize an objective function given by z is equal to x plus y. We said that our standard form is maximize, which means if we have to convert a minimize to maximize, we have to multiply the right hand side with a -1, and the answer will be maximizing objective function. So we get maximize z is equal to minus x minus y. Now let's look at the constraints. The first constraint is, let's say 50x plus 24y is less than equal to 2400. Again, we said that our constraints will not have inequalities, they will have equalities, and we also talked about a slack variable. So that means we have to add a slack variable, we call it as s1, and we have 50x plus 24y plus s1 is equal to 2400. Similarly, if we have a second constraint, which is 30x plus 33y is less than equal to 2100, that transforms to 30x plus 33y plus s2 is equal to 2100. Here is the other way around. So x is given to be greater than 20. In this case, we have to subtract a surplus variable. So we have x minus s3 is equal to 20, and if we have y as an example greater than equal to 5, the transform for that for our standard form would be y minus s4 is equal to 5. And also all x, y, s1, s2, s3, s4 should be greater than equal to 0 in our standard form. So clearly we can see that the left side was a given problem and not in a standard form, and the right hand side is the same problem. It is now converted to our standard form. We will now visit an LP problem that we had discussed earlier and see how do we convert that to our standard form. So we are given an objective function maximize z is equal to x plus y, and the constraints were what we see on the left side, and this was the solution using the graphical method, and we see that the maximum value occurred at x equals 30.97 and 35.48, and the value was 66.45. To convert the same problem to our standard form, the objective function and the constraints are given to be what we see right now on the screen, and their corresponding conversions are maximize is still maximized, so it's going to be z is equal to x plus y. The constraints, we have to add a slack variable to constraint number 1, we'll call it as s1. We have to add a slack variable s2 to constraint number 2. We have to subtract a surplus variable from constraint 3, and same way subtract a surplus variable from constraint 4. Now let's see what is the significance of slack and surplus variable. So we add a slack variable or we subtract a surplus variable. What does that actually mean? So if you look at this graph, our optimal solution falls at this point, x is equal to 30.97 and y equals 35.48. And we also note that constraint number 2 and constraint number 1 are passing through the optimal solution. Our s1 and s2 are the slack variables for constraint 1 and 2, and their final value is 0 and 0. So anytime we have the value of slack and surplus variable as 0, that means that the constraint to which that variable belongs passes through the optimal solution, and hence in our case constraint 1 and 2 are called binding constraints. On the other side, s3 and s4 were surplus variables that we added to constraint 3 and 4, but they are not 0. They have a value of 10.97 and 30.48. So this shows that the two constraints 3 and 4 are this far from the optimal solution. And since constraint number 3 and 4 do not pass through the optimal solution, they are called non-binding constraints. So here is the definition of binding and non-binding constraints. So binding constraints are constraint that holds or passes through the optimal solution, and by changing such a constraint, the optimal solution will change as well. and the slack or surplus variable in such constraint results in a zero value for optimal solution. And a non-binding constraint is a constraint that does not hold and hence does not pass through the optimal solution. And of course, in this case, the slack or the surplus variable is non-zero value for the optimal solution.